Yeah, so I'll be presenting part of my PhD project titled Inferring the Distribution of Fitness Effects Using the Ancestral Recombination Graph. So first of all, what is the DFE or the distribution of fitness effects? It is this statistic, a continuous distribution that quantifies the effects of a new mutation. So you can imagine that you have an individual, and then this individual suffers a de novo mutation somewhere unknown on the genome. And so this de novo mutation has an effect, which we can broadly categorize as deleterious, neutral, or advantageous. But this is a continuous scale, and so it can fit anywhere in this continuum. And this is quantified by a selection coefficient by the letter S. And so, as I said, it is a continuous distribution, and it is of central importance in population genetics because it informs us about how natural selection is acting broadly to influence genetic diversity. And so, because it is of such importance, it is already has been estimated by previous efforts, such as this one that I show you here by Christian Huber and collaborators. So here in the x-axis, we have selection coefficients going from deleterious to neutral and advantageous. And in the y-axis, we have probability. And so what this tells us is that the majority of mutations will be effectively neutral at 0.0 selection coefficient, that very little mutations are actually advantageous, and that the rest are either slightly deleterious to moderately and more strongly deleterious. So this statistic has already been inferred, as I've been telling you, but it's been inferred using summary statistics. So pieces of the complete puzzle of evolutionary history or genealogical history, such as the size frequency spectrum, but also haplotype lengths and a combination of summary statistics. But what would happen if we had access to a statistic that captured the complete picture or the complete genealogical history of a sample of a population? And so we surprisingly we have this, and this is called the Ancestral Recombination Graph. And in case you're not familiar with this structure, it is basically the coalescent model, which gives you the coalescences of a sample population, but with recombination, which is a crucial piece of the puzzle. And so because this is a single graph, it can also be expressed as a collection of local trees among the genome. And so each local tree resembles or tells you the story of the genealogical history of a particular set of a haplotype. And since recombination occurs in the genome, so every time a recombination event happens, the genealogy may change, and we need a new tree to explain its evolutionary history. And so there have been multiple advancements in ARC inference software that I'm going to use to develop a software in order to estimate natural selection using this set of local trees. So the main idea here is that selection influences the topology of these local trees. And by a local tree, I'm referring and a derived allele given in color, which happens after a certain mutation. And so here, the main signal that we are looking at is that natural selection influences branch lengths. So if you look at the neutral allele or an allele that evolves neutrally, this will on average have longer branch lengths than that of a selected allele, which because of the effect of selection, it's causing the branch lengths to diminish or to be smaller. How natural selection is acting. And with this, I developed a model that uses a likelihood approach. And so here, what we are basically doing is counting the number of lineages of the derived allele at a specific time point. So for instances, here at time 0, we have 4 lineages of the derived allele, but at time 1, we only have 2 coalescent events, and we're left only with 2 lineages. And by time 2, the derived allele has already coalesced into the ancestral allele. So this that I have told you can be formalized in a likelihood approach which says that the probability of finding a certain numbers of lineages C of the derived allele, given a specific time point, tells us about selection coefficients. And we multiply this for all time points present in a tree and for all trees, because we are analyzing multiple trees. And with this, we have estimates of particular values of selection coefficients. So these are discrete values. But what we ultimately want to find is a distribution that explains the behavior of these selection coefficients or of these effects. So after following an integration step over all values of selection coefficients, we can find instead the parameters of a continuous distribution that explain the behavior of these selection coefficients. So these parameters, I'm using a gamma distribution, are the shape and scale parameters, will give you the form of the probability that these selection coefficients are going to take. And so with this, here are my inferences. So here in the x-axis, we have the shape parameters. On the y-axis, we have the scale parameters. In the red coordinates is the real parameter values, the one that I'm modeling after. And in black, the black dots are all my independent inferences. So this, it looks good, but we don't have any reference about how it looks like. And if we draw it out, it looks something like this. So here, in the transparent columns is the distribution that I'm modeling after, and in the bold colors is the distribution that I'm inferring with my method. And so as you can see, we have really accurate estimates. These are binned selection coefficients going from weak to strong selection. And this is under a constant population size, but we can also do inferences from more realistic demographic models, such as a population expansion, and also yield very accurate estimations of the distribution of fitness effects. And so with this, I conclude that the tree sequence representation of the ancestral that we are able to develop an arc-based method to accurately infer the distribution of fitness effects, and that the method works even under alternative demographic models, such as a drastic population expansion as seen in humans. And so I want to thank my lab, the Computational Population Genetics Lab, Dr. Diego Ortega, all my collaborators, my PhD committee, and technical staff for making this possible. Thank you.
Thank you, Alan. So we have time for some questions. Right here.
Hola, muy interesante tu plática. Yo tengo una pregunta de ver si en este método no hay como un bias de una observation bias, porque por ejemplo muchas de las mutaciones que se perdieron no van a estar en el RG correcto. Entonces mi pregunta es si esas mutaciones podrían afectar, no sé, los estimados.
Sí, claro. Sí, las mutaciones demasiado deleterias pues no se ven en el muestreo de las poblaciones y sí, pues sí puede distorsionar la forma de la distribución.
Ok.
Aunque hay maneras de controlar para esa situación. Por ejemplo, una es utilizando la proporción de alelos derivados y sitios fijos, que es como una estrategia que se usa en el campo.
Gracias.
Over here. Yeah.
Aquí. Hola, Alan. Muchas felicidades. Está muy bonito el trabajo. Quería preguntarte dos cosas. La primera es, ¿qué es lo que le da más poder el Ancestral Recombination Graph comparado con las Summary Statistics que estabas hablando? Y la segunda es, ¿cómo se puede aplicar esto a genomic data? Me imagino que aquí estás haciendo simulaciones, entonces agarras todo el árbol de coalescencia y con eso infieres, pero también puedes inferir ese árbol con secuencias genómicas, ¿o cómo cambiaría?
A ver, la primera pregunta, el ARG es realmente un estadístico que es capaz de producirte una hipótesis de cómo evolucionó esa secuencia genómica. Y esto es porque incorpora recombinación. Por ejemplo, si tú tomas el modelo coalescente, pues este no funciona para secuencias recombinantes. Para poder incorporar recombinación, ese modelo es capaz de capturar la evolución completa, la evolución genealógica de todos los ancestros, bueno, según tu muestreo. Entonces, en ese sentido, por eso es muy poderoso el ARC, porque potencialmente puedes capturar la historia evolutiva correcta. La segunda pregunta, perdón.
¿Cómo lo haces en secuencias genómicas para inferir
Sí.
estos árboles?
Sí, aquí es un poco difícil porque necesitas haplotipos faseados. Entonces, por ejemplo, hay varios software que te infieren el ARC de datos empíricos y estos requieren típicamente haplotipos faseados. En el que planeo usar yo se llama Relate y esa es la metodología que uso, que puedes partir, por ejemplo, de un BCF.
Y tienes que tener muchos datos, así especialmente de muchas poblaciones para poder, de la misma población para hacerlo.
De la misma población, sí, y en teoría un gran cacho del genoma, lo más posible.
O por lo menos que sean el mismo espacio del genoma,
sí,
¿verdad?
Exacto, sí.
Muchas gracias.
A quick question from Jack.
Thanks, it was very nice. Presumably you're doing all the analysis under a genic model of selection, and I'm wondering if you could incorporate stabilizing selection into the ARG, or is that somehow already incorporated into your analysis?
Yeah, so for positive selection?
Stabilizing selection.
Well, here we're modeling only the deleterious portion. This is because well, the literature has shown that the positive portion is very rare, so we're interested more in the deleterious side. But I guess we're only modeling selection coefficients. Does that answer the question? Thank you.
Thank you. A round of applause for the speaker.